Okay, so we'll go back to another video. So today's integral we're dealing with is we want to find a nice little closed form of the following. So we have from 0 to pi over 4 of tangent to the power n of x plus cotangent to the power n of x dx, where our parameter n is following in between from the range non-inclusive from both sides of -1 to +1. So the video itself for today is actually not going to be too bad because a lot of this stuff just utilizes some u-substitutions. And once we come to a step, it actually might question, you might be thinking that how come we actually did something like this? I will let you know when we get to that point. But then afterwards, doing so, we're actually going to be utilizing two special functions. So I'll just say it off the bat. We'll be utilizing both the beta and the gamma functions to help simplify our answer to our closed form. So everything, and I should also mention that n in between -1 to +1, that's of course the reals in between there. So I should have specified that beforehand. But anyway, with all that being said, why don't we actually just jump right in? So let's do our u-sub. So we'll let u equals tangent of x. So that means differentiating both sides. So I have du is going to equal secant square of x, then dx. Now if I substitute this back in, so our new integral, if I plug this, so that means 0 for x is going to be 0. If I plug in pi over 4 for over here, that's going to be 1. And so what I have is that now this is actually going to be, so u to the power n, and then plus cotangent, where cotangent to the power n, that's the same thing can be written as 1 divided by tangent of x, well, to the power n. So in other words, I can actually write this as u plus u to the power -n. And then don't forget, I have our du substitution, our differential that we have to substitute. So what I can do is actually just divide the secant x squared to both sides, and then that means we have du divided by secant square x. In other words, that's the same thing for the denominator as 1 plus tangent square of x, which can be written as the same thing as 1 plus u square. And so we have du. Okay, so let's now perform yet again another u substitution. So we'll let now u equals 1 over t. And so du is going to be -1 divided by t squared and then dt. So now this means our new integral we're going to have over here is that this is actually, so I plug in 1, so that's going to be 1. Now if I plug in 0, that's undefined, but if I were to take that as a limit, that's actually going to simply approach positive infinity. And so we yield the same thing yet again, so on the numerator, so t to the power n, or in other words, I can actually write this as a better way of how it's written as follows. So t to the power -n, and then add this with t to the power n divided by 1 plus, so let's see, u squared, so that means that's going to be 1 divided by t squared. And then back in, we just substitute the du over here, so that means it's going to be times -1 divided by t squared and then dt. And so we can simplify this down such that if I switch the bounds, so that means that's going to be negative, but then that negative cancel itself, then I'll just multiply the t squared and everything back into over here. So now we have our new integral of 1 to infinity of t to the power -n, and then plus t to the power n, then divided by t squared and then plus 1 and then dt. Okay, so we've come down to the conclusion that we can actually write this, our given integral, in the two following integrals over here. So why don't I actually take this integral over here, so I'll call this integral number 1 and then integral number 2, and we're actually going to add these two together. So that means now that, so calling our integral, we'll call this capital I, so if I actually add 2 times I, which because they're the same thing written as differently, so if I add integral number 1 and integral number 2, so that means we have that this is actually just going to be 2 times I, and then simply just equal to, so they share the same integrand, but we actually now can combine our bounds. So now that our bounds is going to be from 0 to infinity, and it's a dummy variable, so I'm just going to go back to u, so it's u to the power n, and then plus u to the power -n, and then divided by u squared, and then plus 1, then du. All right, so now going back, let's perform another u substitution for the third time. We're going to let u equals tangent of x, and then back again, so that means secant square x and then dx. Now plugging this back in, so let me actually switch to a different marker for this one. So now I have that 2i so far is, now plug in our new bounds over here, so let's see, I have infinity, so that means that's simply just going to approach pi divided by 2. If I plug in 0, so that means that's going to approach 0, so it will equal 0. So I have pi divided by 2 and then 0. And then now we just put this back in, so tangent to the power n of x, add this with tangent to the power -n of x and then being divided by, so that means tangent square of x and then plus 1. That's the same thing as secant square x, and then multiply the differential, substitute that for the du, so times secant square x and then du, or rather d or dx. I don't know why I got the variables mixed up. So as mentioned, you might be thinking, because if I were to simplify this down, now I have the integral from 0 to pi over 2, and then now tangent to the power n times tangent to the power n of x, and then add this with tangent to the negative n of x and then dx. So you might be thinking to yourself, this looks like just the exact same integral as what we started. You just went back to square one, right? So no, we have our bounds from 0 to pi over 4, and then we have from 0 to pi over 2. So someone might be thinking, you might be thinking to yourself, couldn't you actually just make this a little bit simpler and then use the idea of the symmetry? Usually that's actually a trick that you can do to rewrite things a little simple. However, not in this case, because both tangent and cotangent are actually odd functions, which that cannot be utilized to utilize the halfness or the double of our values. So that cannot work. So we have to actually utilize this little trick over here to get what we need. So just to clarify everything, our bounds are different, even though the integrals or integrands are the same. So we did not actually skip a whole lot of process. This is actually what we need to do to actually achieve what we want to get. So with that in mind, so now let's actually now convert this. Well, not convert yet. Let me actually now split this using the linearity. So we're actually going to use add two different integrals. So pi divided by 2 of tangent to the power nx and then dx. Add this with the integral from 0 to pi divided by 2 of tangent to the power negative n of x and then dx. Now what I'll do is now let's actually convert this such that we'll be utilizing both the sine and cosine functions from our integrand. So now what this converts to is that now I can actually write tangent of x. Of course, to reiterate, tangent is the same thing as sine divided by cosine. And of course, with tangent to the power negative n, that's the same thing as 1 divided by tangent of x, aka cotangent. You just flip it so it's cosine divided by sine. So pi divided by 2. In other words, over here, this is actually written as the same thing as sine to the power n of x multiplied by cosine to the negative n of x and then dx. Add this, so 0 to pi over 2. This one over here is going to be sine to the power negative n of x and then multiply with cosine to the power n of x and then dx. All right, so we have this in mind. So now keep in mind that now we're actually going to be utilizing the beta function, and the beta function specifically says that if you have two inputs for x and y, so I'm going to put this note over here. So beta of xy is going to equal to the following integral representation. It's going to equal to 2 times the integral from 0 to pi divided by 2 of sine to the power 2x minus 1 of theta, and then cosine of 2 to the power y minus 1 theta, and then d theta. And then let me actually write another function we'll be using, well, in terms of the gamma relation. So beta of x and y, that's the same thing as written as gamma of x, then times gamma of y, and then divided by gamma of x plus y. We'll just write this in handy just to get everything what we need. Okay. So now if I put everything back in together, so we actually plug in our parameters correctly. So we have that so far. To reiterate, 2 times I is going to be rewritten as the same thing as 1/2 times beta. Now our following input for this one specifically is going to be 1 plus n divided by 2 and then comma 1 minus n divided by 2. Okay, and now add this again. So 1/2 beta of now just basically just switch. So it's 1 minus n divided by 2 and then 1 plus n divided by 2. Okay. So now with this, now we can actually just utilize the beta function over here and then use this in terms of gamma. So if I actually plug our inputs for gamma over here, x and y, back to the bottom, we actually get that this is actually just going to equal 1. So gamma of 1 essentially is actually just going to equal 1. So you could actually just plug in that number in utilizing its improper integral representation. So that means the denominator is just, it gets rid of that. So now what we're left with, so is going to be 1/2. So now we have gamma of 1 plus n, then divided by 2, times gamma of 1 minus n divided by 2, and then do this again for this input over here, so plus 1/2, and now we have gamma of 1 minus n divided by 2, and then multiply with gamma of 1 plus n divided by 2. And if I just combine all this together, we have that this is actually just going to equal just 1. And so it's gamma times 1 plus n divided by 2 multiplied by gamma of 1 minus n divided by 2. All right, And so one more thing we're going to be using for the gamma relation is using its reflection formula, Euler's reflection formula, which says that gamma of n times gamma of 1 minus n is going to equal to simply just pi divided by sine of n times pi. So if we actually use our inputs correctly, we'll be using the following input for 1 minus n divided by 2. And so if I actually just plug this back in, so that means now, I'm actually now putting a different marker for this, we get that over here that this is actually just going to equal pi and then divided by sine of pi. And then I said we'll be utilizing 1 minus n divided by 2. So 1 minus n divided by 2 over here. And then if I actually just plug this, well, not necessarily plug this in, you can actually see from both sine of pi and then distribute the pi into there. So I have a pi half and then minus pi times n divided by 2. You can actually use that symmetry for, well, not necessarily symmetry, it's more of a phase shift of the pi over 2. You can actually rewrite this the same thing as pi divided by cosine at pi times n divided by 2. So that means this is equal to 2i, and so therefore if I just divide 2 to both sides, in other words, that could also be written as the same thing as pi times secant of pi n divided by 2. So if I actually just divide the 2 to both sides, so now capital I, which is our integral we want to calculate, the closed form, is the same thing, is going to equate to pi divided by 2 multiplied by secant of pi times n and then divided by 2. And so with that, that's our nice little closed form for our given integral. Our parameters we're dealing with is the real numbers between and non-inclusive of -1 and +1. And so you just plug in whatever numbers in between that range and you actually get that value. So with that, we are done. And we actually, utilize our special functions over here for both gamma and beta. And that was like, what, 3 times we actually did u-substitution. So yeah, I did mention there was going to be a lot of u-substitutions involved. So yeah, that's pretty cool if you ask me.